only. So that was, I guess, the question similar to exercise number 3, right? So let us work it out with given mean, which is 172 and standard deviation of 29. So mu, right? 172. Sigma standard deviation is 29. Also, we had the same sample size n, and that number was equal to 64. And also, there was a value of x that I made up, and it was 180. So this is my formula here that we're supposed to utilize. Find z-score as difference x and mean divided by a standard deviation over a square root of n. So let me plug these numbers given in it and produce the quiz answer. So just carefully put all of these numbers in. 172. Then we divide this by 29 over a square root from 64. So then we're gonna have the parentheses around our numerator as well as denominator, like that. And I guess we're gonna need to go ahead and use our calculator, right? So I'm gonna get the scientific calculator typed and select that favorite Desmos tool. And then we're going to use parentheses for numerator. 180 minus 172. So I guess most people did it perfectly correctly. And if you missed something, well, then advice is use the same calculator. If you have preference for something else, make sure that you use it right. So here's the z that I found, and it is 2.20 something. Some people put 2.2. Well, it was okay. We usually round this to 2.21, right? Because the following digit is 1. But since we didn't have to do anything with this z-score on the next step, then it was fine if you just leave it as 2.2. So anyways, we are going to do the problem that will better reflect of what's supposed to be done here. So maybe exercise number 7 that could be used in the real life situations. So they're talking about ejection seats for the airplane. So they say they used to be designed for men, and now they check and see if for women these seats were also going to work. So population of women in exercise number 7 has its mean equal to 143 pounds and a standard deviation of 29. And then I'm going to need to put this probability question in, right? So they ask in the part A to find the chance that the woman selected will have a weight in between of 140 pounds and 211 pounds. So this is what we have for the question. And as usual, I'm going to make a picture here and then get mean of 143 right in the center, right? So we have 140 on the left side and 211. That's all the way on the right. So it looks like this population is kind of shifted towards the right direction compared to the actual mean. So question is, how can I find the area under this curve? And our standard way of converting to the z-scores my values of x. So I'm gonna get corresponding to 140 value of z, as well as corresponding to 211. And here's the formula. So we're going to use that formula to find our z-scores. So we're going to have to get those fractions, and on the top, we're going to put differences with mean and our x values. So 140, excuse me, subtracted mean, which is 143, right? And divided by a standard deviation. Sigma was 49, and divide by this square root 29 by square root extracted from number 1, because n, they say, in this exercise is equal to 1 because one woman was selected. So I just put that 29, let me write it better, divided by square root of 1, which actually just a 29, right? But you could utilize that formula if you like, and make sure that you have parentheses around your numerator as well as denominator. So let's calculate this. So I'm going to get this 140 minus 143 in the parentheses, right? And then we divide this by another parentheses with 29 over square root of 1. So here's the z-score that we produced. It is negative something 1, 0, 3, etc. So we use negative 0.10, right? Because we always round to the nearest hundreds. So similarly to this, I'm going to get another z-score. So I'm going to say this is a first value. I put index 1, and the second value I'll put with index 2 that corresponds to the bigger number. And the same exact procedure is here. So I put 211, I subtract 143 in my numerator. And for denominator, it's still 29 over radical 1, right? So you could put radical 1, or you don't have to, it's the same thing, but I guess just to be on the safe side, sometimes people say. So let us do this again. Please notice that you need to be very comfortable using your calculator. So I advise you to use that Desmos. If you prefer some other calculator, it's up to you, but make sure that you can do these calculations correctly. That's the key part here. So one more value of z is found. It is 2.344 ... So we need just 234, right? And now we will be able to answer question about probability by finding the area in our favorite tables. So it looks like there is a negative value of z and a positive value of z. So I'm gonna have to use 2 pages. So for first one, I'll use negative, and the negative is 0.10. So I need 0.1 or 0.1. And since 0.10 has only 0 hundredths, I pull this number from my first column. So 4602 is usual area from the left side, and therefore I'm going to be able to put this here, 0.4602. So little tail, people say, is found, and now I need to find the other region, the bigger one, right? So I'm going to have to go to the positive z-scores, and I will, for that matter, scroll down, because the other is 2.34, right? Was 4 hundredths. So 0.04 is the column, and 2.3 is a row to use. So right on their intersection, I have another area, and this is going to be the big one. So this is going to be the one that we have from the left side, as usual, up to that particular point. So here's our big area, and it's 99%, 0.9904. So to get the area we need, the one in between, we always subtract, right, from the big one, the small one. So whenever you have 2 z-scores, turns out in all problems here, you will have to always subtract those corresponding areas and see what you produce for the answer. So it looks like little by little, when I subtract, I get something like about 53%. Only 53% of women will actually fit into those seats that are designed for males in those airplanes. And that's not really a big population, right? Looks like women on the lighter side are not going to be happy with those seats. And that's probably something that will make them to reconstruct those seats. Well, there is a part B here that is more related to this particular section that says, what if you also have a sample size of 36? So now instead of dealing just with a 1, we have 36. So looks like this is going to change our formulas, right? So I'm still trying to find the area that deals with those 2 particular values, 140 and 211. So that's the same exact picture. So I need to find the area in between, but corresponding z-scores are not going to be the same, right? So for the first one, I'm going to use exact same fraction. So 140 minus 143. So I'm looking at the here, the left side on the bottom, and I divide this by 29, right? But then I have to put a square root extracted from that 36, right? And we'll get the z-square. Analogously, for the second one, we also get same exact numbers like we have for Z2. There are 211 minus 143 over 29, but once again, this is going to be divided by that square root extracted from number 36. So we're getting closer to the result, and please notice when I start to calculate, I could just go to the same exact entries that we already had utilized and just to added those. So I could just added those previous calculations by simply highlighting that 1 in denominator, right? And placing 36. And the same thing I can do for the other side, and that's advantage of using that particular calculator. So I got pair of z-scores without re-entering anything, but just by taking this same calculations and changing them a little bit. So first is 620, actually that's the second one, it should be. No, that's the first one. So 620 and 6, so we actually care only about negative 0.62, right? So the corresponding z will be a negative 0.62. So the picture is the same, it's just z-scores that are going to be changed. And then for 211, I get a 14. That's a huge z-score, right? It is the largest we working with is actually 3.5. And here's, if I round it to nearest hundreds, be 14.07. Okay, so let's see what happens now. Let's see what our tables are going to say about those areas. So it looks like we're opened on the positive z-score part, and z-score that should correspond to my 14 is not appearing here because the table ends at 3.5, but it actually says 3.5 and up. So all the areas we treat the same after that upper part. So we say that area has to be 0.9999. This be a big area that corresponded to that z-score on the right side. And then similarly, I will go for the second area and then subtract it from the first one. So it looks like the plan is always the same. So I need negative 0.62. So on the next page, actually on the previous page, I have negative 0.6 right there. And then the column 0.02. So right on the intersection of this, I see the value. It is going to give us this little tail that we don't really need. This be a 0.2676. And then, just like in the previous part, I will be subtracting these two areas and get the answer for that part. So it looks like we're producing something like 0.7323, which is much bigger chance, one can say so. It looks like there's actually more chance that a woman pilot will fit into this particular seat. But if you start to think of what is happening here, then you probably noticed they're actually taking 36 women and their average weight. So how can you, in practice, utilize the average weight? You have a woman and you have a sit and you see if that's a good sit or not. But what's the average weight? We don't put 36 women, right? So looks like that part does not really make much sense in practice. And that's exactly what part C of this exercise is asking you, to see which part makes less sense. And I would say that's part B, right? Because in practice, you can just deal with every woman pilot separately. So sometimes it makes sense to do the average, and sometimes it does not. Well, this process totally repeated what we had done last time. So just little different numbers, but we're still using that same z-square formulas, right? And I will take a little look at the last section of this chapter 5 that we need. It's going to be the approximation by binomial distribution. So you probably already remember a pair of formulas that we had used before for mean and for standard deviation. And it turns out if you're not given the mean and standard deviation, then you can use these formulas to find those for the so-called binomial distributions that I saw in the previous section, nicely pictured. Let's see here. Looks like the picture of these bars kind of goes under the normal curve, right? And that's what they're actually talking about. So if you don't have the normal distribution, but this so-called binomial distribution, then using these formulas, you can approximate this bunch of bars with the normal distribution, and then use tables and continue with the story. So the difference with binomial distribution is that you have only whole number of successes or correct guesses. So you can only have 3 successes or 4 successes. You don't have 3.5 of those successes. And that's the reason why here they have this either 3 or 4 or 5, but we need this continuous, this normal distribution. So we must do the approximation. And when you approximate, the section 6 of chapter 5 actually says how to do the process, and it gives you a definition that is very important, and that's what I want to get used to today. So they say you must use so-called 0.5 increments, x plus 0.5 and x minus 0.5. What does this mean? Well, when you're looking for some probability, like for example 120 here in the picture above, then notice they surrounded by 119.5 and by 120.5. So that's where these 0.5s appear. So we're never going to use actual 120. We either use one or the other piece that surround this number. So I guess to better illustrate it, I'm going to look at the exercises at the end of this section and start to get used to approximating with this 0.5 increments. So let's take a look at exercise number 1 that says more than 15 people in prison find the probability of that, and this means that x is more, right, greater than 15. And then I want to approximate this with this so-called normal distribution. So we get a bar that corresponds to 15 people. Then we can have next 16. And the previous will be 14. When you say actually there is another previous 13. Well, yes, but we only care about numbers that surround that 15. So if someone says more than 15, it means we're greater. So it could be 16 or it could be 17 or more all the way to the right. And I don't really care how far to the right we go. I just care about this border value, where the region actually starts. And it looks like it starts at the right side of the bar with number 15. So there is a point 14 and a half on the left side of this bar and 15 and a half, which is on the other side. It looks like we're exactly at that 15.5, and that's what I'm gonna write in here. X is greater than 15.5. You see, I did the approximation, and then we could just continue with the process the way we did in a previous section. So once I know my X value, well, then I start doing the same exact procedure that we already done today and last time. So today's our goal to get used to this approximation. So let me try another exercise. How about problem number 2 of the same type? And that 2 says, find the probability that at least 24. So probability. Now here comes our familiar word, at least. Remember what that was staying for? It means not less. So X could be only greater or equal. At least 24, so greater than or equal to 24, just like that. So I'm going to picture this with a bunch of bars, such as 24 here. There's also 25, the bigger one. So the bigger one on the right and the smaller one on the left. That's all I really care about. So we need to now decide what is going on with that picture. Well, we have here equal sign, right? It could be equal to 24. So I include 24 with the bar that corresponds to it. Or greater means we can also continue all the way to the right. So here's 23 and a half in between of 23 and 24, and 24 and a half in between of 24 and 25. It looks like here we have the border. You see that border? That's where the pink starts. And this corresponds to 23.5. So here's my approximation. X is greater than or equal to 23.5. So that's all I need to get started. And that's what these exercises are actually asking me to do. So I'd like to do one more exercise, like number 5. And then you can do a little quiz, like exercise number 3, for instance. So I'm going to do number 5, and you can try number 3. in exercise number 5, they say, again, find the probability that no more means greater is not allowed. Well, then it should be less than or equal. See, in this exercises, we pay very close attention to this equal sign because it makes difference if we include or we don't include that particular bar. So here I put those numbers 3, 4, and 5. Again, 4 is in the middle, always in the middle, because we need to see if we include this 3.5, so always 0.5 or 4.5. And to see it again, I'm making a picture. I'm going to get that equal sign, means we take this whole bar with 4 or smaller, so we go to the left. Well, the border is right there, right? Because 4 is included, so it's 4.5. And that's my approximation. So we get a x is less than or equal to 4.5. At that stage, we're done. So all equations here, they just ask to turn the probability they asked about into the probability with this 4.5 or 23.5 with this 0.5 increment. So the question to you, how about exercise number 3 for a quiz, a little quiz for tonight? So can you also tell me how you're gonna approximate this? So they asking about probability of fewer than 100. Fewer means less. So I'm gonna help you a little bit. I'll write this down. Less than 100. So the question is how you're gonna round this with the 0.5 increments. Like, is it 99.5 or 100.5? And that's all you need to do for this quiz. Just put this in the chat, the answer for that.